So today will be probably our last lecture because our formal lecture with quantum optics and quantum information has ended last week. That's our regular lecture. And today we're going to talk about something for the bonus session, the Deutsch algorithm. So we're going to explain how quantum algorithms work. And if I can manage to finish it today without taking 3 hours, then this will be our last lecture. Then next one, I know the next 2 weeks are final weeks, right? So if I can manage to finish Deutsch algorithm today, then the next session will be a talk. It won't be a lecture. It will be a talk, and I will share with you some current research on MV centers and single-photon quantum communication, I guess. So something that combines our two labs and related to the current research, so that you can see that what you learn right now is actually very relevant to what's going on right now in the world. And then after that will be the final week, and hopefully we won't have any lecture that week, and you can focus on your finals. All right, so Deutsch algorithm. So today's talk is going to be a little different from previous talk. Previously, we focused mostly on physics, right? But today we're going to talk about algorithm. And algorithm is basically another name, I would say, in my interpretation, is another name for recipe. Recipe. Is that how you spell? Or recipe. Okay. I hope my spelling is right. Yeah, could you check for me? So it's another name for recipe. That means it is a series of instructions for you to do something, to achieve some purpose. Right? If you have, is that right? Okay, so just RECIPE. Okay, thanks. So if you want to learn how to make cake, or you want to make how to make baozi or dumpling, yeah, baozi. Yeah, it's actually an English word, baozi. You will get a recipe, and it will tell you what kind of ingredient you need and which portion you need to mix them and bake them or steam them for like how long. There's a series of steps you need to go through in order to make a delicious dumpling or baozi or cake, right? So algorithm is for the same purpose. It's a recipe for a certain problem, a certain kind of problem. And this particular problem that we're going to talk about is actually pretty simple. But to demonstrate this problem, to demonstrate the quantum advantage in this problem is important. And Deutsch algorithm is the first quantum algorithm ever proposed, like the first one proposed. And that's why it served the purpose of illustrating why quantum computing might be more powerful than classical computing, okay? All right, before I start, I want to briefly mention something that I told you last week. Remember I told you that a quantum function, a quantum or quantum processor cannot just have one input. It needs to have two input, right? So typically a classical computer, so this is a quantum computer, but say this is a classical computer. A classical computer, a classical computer take an input, right? Or several input, but you can take one input at a minimum, and it give you an output, right? For example, if you want to calculate the exponential function of 201, right? So you type 201 in, and then the computer will give you exponential 201, and this will be a very, very large number. I don't know, maybe 10 times to the, I don't know, like 100 power or power of 100 or something, right? If you have enough digit to show this number. So that's what classical computer can do. A most basic or fundamental quantum processor, or this is a classical processor. A quantum processor cannot take just one input and give you an output like this. Why? So let's first get this straight, then we'll move on to the algorithm. And this is actually very important to understand. The reason is all quantum processors are made of unitary transformations, right? Some kind of physical operation that is unitary. If it is not unitary, it will not conserve the total probability of your wave function, and then everything gets screwed up, right? So rule number one for quantum mechanical operation is you need to conserve total probability. Like that's the most fundamental and basic things to achieve, right? But somehow this scheme, this single input, single output scheme, contradict with this requirement of unitary transformation. Why is that? Let's see. If you have two numbers, okay, A and B, and let's say they are different. Let me just give them numbers, 2 and 5. Yeah? And say they map or through this quantum function. Okay, let me just put Q here to symbolize, to indicate this is a quantum function. Through this quantum function, you get A and B. And suppose they are the same, which is pretty common, right? You can have a function that looks like this, right? And then say you have like same value here, and if you pick two numbers here, they give the same value, right? And if you pick another number here, they give different value. Function can have all kinds of shape. Yeah. So suppose this is the case. What will happen if we want to inverse it? So if we suppose that this transformation is unitary, that means you can take this. You can take this and put this at this input, right? And it's supposed to give you what? If we assume, so this is a proof by contradiction. So if we assume that the inverse is the same as that, so this is a condition for unitary transformation, right? If you take this as your input, what will it give you? Supposedly, we hope it will give us this, right? Yeah. But now we do this. We also do this. We take this as input, and supposedly we hope that we will get this. Yes? Get B back. Okay. Now the problem here is, since FA is equal to FB, so when you are doing this input, you're basically doing the same as this. If you put in F of A, is equivalent to putting F of B, yes? Now, if F of A, after this quantum processor give you A, what does this give you? Because this is supposed to give you B. right? They are the same input, but the output is different. You see? One input mapped to two different output. That's not how a function works, right? A function cannot work like that. You get one input, you can have many input mapping to the same output, but you cannot have one input mapping to several output. That is just crazy, yeah? Therefore, you see how this contradicts with the assumption of a unitary transformation. And that's why quantum process intrinsically cannot manage this. This cannot be done with quantum processors intrinsically. Okay, it's not a matter of preference. It cannot be done. Okay. So, therefore, what's the way out? What's the way out? So people who study computer scientists, they're very, very smart. Maybe, I don't know. Maybe a physicist think of this. I don't know. But one way to get out of this is to entangle this with the input. Okay? So if your output, for example, is an entangled state with your input, then that won't be a problem. Okay? Why? Because in this case, you have A, so state A, going through this quantum processor, and you get A and FA. Yeah? Yes? And B, you get B and FB. Even if these two are the same, they are still different because they are entangled with A and B, right? So they are not the same, even if A and B are the F of A and F of B are the same. Okay. So this is just the idea. So how do we actually accomplish this? Well, first of all, you need two input. You need two input for your quantum processor. Okay? So let's call it X and Y. Yeah? And then your output will be also two because you have entanglement, right? You have a product state. So you'll be an output. And this port, so here you have, so this port somehow will contain the information of the function. And it looks like this. Okay? So this is how you do it. And if you set y equal to 0, right? Then you will have this 0, this f of x, and 0. Yeah? And what is this? This is modulus 2, right? You see? Here's your product state. This is your product state. Okay? So that's how you do it, by construction. So some people who are very smart construct this scheme for quantum processor, and that's like the most fundamental, the most basic quantum processor you can have. It must have two input. Okay. All right. So something I want to put something here about the modulus 2. So if you have a qubit that is modulus with 0, right? So so like right here, we only talk about qubit. So any numbers that you see, including functions, can only take value of 0 or 1. Yeah, of course you can have superposition, but within the bracket, it can only take the value of 0 or 1, right? So anything that is added with 0 and modulus 2, it is the same as itself. Yeah. So we can try, put 1 here, that'll give you 1. Put 0 here, that'll give you 0. Yeah. Anything that is modulus with 1 will give you the inverse. Okay, I use this bar, this overhead bar to denote inverse. So try that again. If we put 0, that will give you 1, right? If we put 1, that will give you 0. Okay? Anything that is doing the modulus with itself. So like again, you just use 0 and 1 because there are only 2 possible options. So it's not too hard to do it. 0, 0 will give you 0. 1, 1 give you 0, right? So that's 0. Okay? So this this cheat sheet will be helpful later. Anything with its inverse, 1. Yes, correct. Yep. All right, so let's keep this cheat sheet here. So if you see this, you immediately know that this is the same as that, right? Right. So let's do a little practice because we're gonna do a lot more later. So let's just do a little practice and to show that this is indeed. So like earlier, we have problem with unitary. Yes. So let's see now we're using product stand. Let's see if the unitary issue can be restored. If the unitary property can be restored. Okay. So let's again start with. So the problem is so the problem is show if I do the inverse of this. No, I don't do the inverse. If I just send this back to the machine, to the quantum processor, the same processor, right? I need to show that it will give me back to this. And by showing this, then I can prove that this is the inverse transformation. And therefore, it's unitary. Okay? So I'll do a quick. So today we're going to do a lot of algebras. Yeah? And it is necessary because this is basically some computer science lecture, not a physics lecture. But it's important to understand how this recipe works in case you are working in a quantum computing company someday. Okay, this will be very helpful. I assure you. All right, so let's just start with 0. Okay, let's start with 0. What does it give you? This, and this is nothing but f of x. Yep. Let's try to reverse this. Yep. Yeah. conjugate transport. Oh. You mean this? This is the unitary condition? -1. Oh. Let's see. Unitary. Let's see. We have Hermitian. So this is Hermitian, right? Oh yeah. All right. Thank you. So she just pointed out that unitary condition should be this. This is called the unitary condition, right? So why do I write this? Am I making a mistake? Maybe. Let's see. We know that the quantum operator must be Hermitian too, right? In order to have an observable. Yeah. Have you seen a non-Hermitian quantum operator? Non-Hermitian transformation? Have you ever seen that? Yes, in an open system, in the open quantum system, that kind of thing exists. So if you want to discuss problems like spontaneous emission or even the coherence, yeah, that's where non-Hermitian operator will come into place. But they are not the standard object in quantum mechanics. They are sort of like the adds-on, okay? Phenomenological terms, phenomenological operator that is invented to explain certain phenomena. Okay, so they are not in the original box of quantum mechanics kit, okay? So in a standard quantum, and of course in computation, you always want this, you want the standard one, because non-Hermitian is will leak energy. It's not energy conserving, and then all hell breaks loose. So you definitely want a Hermitian. So if you have a quantum operator, then it's basically Hermitian. Okay, so this is almost like an intrinsic property of quantum operator. And now you're adding this unitary thing, right? If you have this unitary thing, then that will imply the modulus will be this, which is 1, right? So this is, that's what I'm talking about here. The reverse is itself, okay? And usually we don't think about this too much, but you're right, yeah. Formally, we should consider both conditions, and together they give this. Yeah, okay, cool. But thanks for the question. All right, so let's come back to this. So let's take this thing, like what we did here. Let's feed this into, let's just feed this value. Let's create another input that looks like this, okay? So if this is the value of 2, and this is the value of 10, let's just simply put 2 and 10 into the quantum processor. Yeah? According to the operation defined here, then it will be this. Yes? What is this? You. Miss Tin. What is this? Look at the quantum cheat sheet. Yes. Huh? Oh, you just try by example. Let's put 0, put 1, and see what you got. Because it can only take 2 values. So it's not hard to exhaust all your possibility. Okay? A is just any input that take 1 or 0. And like I said, the qubit can only take 1 or 0. Yeah? So this algebra is very different from what we usually do, right? Because usually when we talk about x can be anything, right? 0.1, 1,000, it can be anything. No, but in this computer science world, it can only take 2 values, very, very limited, 1 or 0. So you basically just substitute 1 and 0 and see if you get a consistent result. Okay?
I think she meant the operation.
The operation?
Yeah.
Oh, the operation means modulus. I thought I talked about this last time. So this means modulus AB, and this means you take the remnant residuals of A. Oh, this is modulus 2. Okay. Oh, sorry. So this is wrong. This is sum and modulus with 2. Yeah. So basically, you take the sum divided by 2, and you take its not real part, but the residual. Okay. So the residual can only be 0 or 1. Correct. So this can assume value of 0 or 1. Yep. All right. So okay. So this is 0 according to our cheat sheet. And that is exactly this. Yes? Okay? One more example, then we're done. We finished the proof. Like I said, it's not hard to exalt all the possibilities. 1. Yeah? If you read a book, they will use very, very fancy math, and you will not know where they come from. Yeah? And often when you go through this very tedious math, you can understand that what they write is actually a summary of what's going on here. It's not derived per se, mathematically. It's basically a summary of exalting all the options. Okay? So rather than doing very fancy math, let's just do this. I like it. I like this way. It's more transparent. So who can tell me what this is? Really? Seriously? 0?
If the first one is true, flip the second.
No. This is just like a sum modulus 2. This is not like a controlled operation. Okay. Refer to the mighty cheat sheet, guys.
Yeah, but like first one is f of x, right?
Yeah.
So the output should be not f of x.
Right.
So it should be 0.
You don't know what f of x is. Right? But it's basically the not or the inverse. Yeah? This guy. Yeah. So I told you this will be useful. All right. So that's okay. So that's this, right? That's this. So let's try to feed the output back to the machine or the processor. Sometimes I write AF, sometimes I write UF. They're the same. Okay, don't be confused. Okay, so I do this. Yes? Anybody get confused? Are you following? I know this is super boring, but are you following? Okay, I'm just taking this. This is the B, right? So B here. Sorry, this is Y here, and f of x. I'm just following the function. Okay. And Mark, what's this? Yes. Yes, thank you. 1. Yeah. Look into the cheat. Use the cheat sheet. Okay? So that's 1. So this is identical to its input. Yeah? Therefore, we show that this machine is its own inverse. Therefore, we show this. Okay? Yeah. So this just shows that this construction works. Can there be other constructions? Maybe. But this is like the bare minimum you need to have as a quantum processor, and it works. Yeah? The operator is anything that has a unitary property, and any quantum transformation. Why does it need 2 input? Because we just show if it has only 1 input and it gives a state like this, right? Then you will have contradictions. One value will map to 2 different values. You have contradiction. This construction is contradict with the unitary property required for quantum operators. Yeah? Let me just write it down in words. Single input, let me just call this single input architecture or construction. Okay? So if I will be writing a proposal, I will use the word architecture. But now I'm just teaching, so I will just simply say construction. Okay? So you construct a quantum processor, single input construction of an quantum processor contradicts with the requirement of unitary transformation. Okay? Yes, we want something that turns x into fx, but we found that single input cannot do this. And the way out is to make this a product state instead of a single qubit. So product means 2 qubit state, right? So the only way out is to, or not the only way, a quick way out is to make this a 2 qubit state instead of a 1 single qubit state. And that way we can avoid this problem of 1 input matching to different output values. Okay, so basically a 2 qubit state is what we want. And how do we construct a 2 qubit state? You cannot have a single qubit input and have a 2 qubit state output, right? So you probably can see that you need at least a 2 single qubit input to give you a product state, a 2 qubit output. And this is one construction. This is a 2 qubit construction. one of the most basic construction, okay? And we're showing here that this is not contradicting with the unitary requirement. Therefore, this is a legal construction for quantum processor, okay? So any quantum processor, this is different from quantum gate, okay? Quantum gate is a different business, okay? Quantum processor describe a function, like mathematical function. It has mappings, okay? So a function, gate just transform a qubit to another qubit, yeah? And it's reversible, right? But a processor transform, take a bunch of numbers, any numbers from a set, okay? And map to some other numbers, okay? Or the most basic, 0 and 1. They can do this, yeah? This is a quantum processor, okay? All right, so with these steps is that. Now, if we now appreciate a little more this form of quantum processor, now we can start to talk about Deutsch algorithms. I have not told you how to construct a processor like this. We will talk about that in the second half of the lecture, optical implementations. There are other implementations using superconducting qubits, trapped ions, neutral atoms, all kinds of stuff, okay? And optical implementation is probably the most basic one. She is bringing up a point. So he's saying the condition for unitary is okay to require this condition at the processor level because proper processor contains many gates, consists of many gates, right? But he's saying that perhaps at the single gate level, it is not required. That's your point, right?
It's not required that there will be permission. It must be unitary. The gate must be unitary, but not permission. But I think
not permission.
Yeah, like basically, you like we put the
Oh, you're right.
and for twice there, you will not come back. You will be another state. Yeah, so it's not permission.
Okay. Okay, I see.
And the question is that your meaning is that the whole process after the whole process, they will see as permission and unitary.
Right. So I probably should phrase it differently. Okay, you're right. So Mr. Xi told us that you can have a gate. Is all gate unitary? Sorry, is all gate unitary?
Yes.
Okay, so let's see. So if I have a state, okay. So if I have a state, this is a gate. U is a gate. Gate. If I have a state, and then give me an output, right? It has to be unitary because this and this needs to be 1, right? You need to conserve probability. If you are starting with 1, your output also should have the same probability, right? Okay, so let's see. So from this requirement, we see that you have this, and you reverse it, you have this. Yeah? Yes? And this needs to be 1, right? And that means this needs to be this, right? So if this is that, then I can multiply this by, on the right side, I can multiply this by the inverse. Yeah? And this is that. Yeah? Because this is 1, right? Yeah? All right, so this is the so-called unitary. Okay. Unitary. How about Hermitian? Hermitian means, so basically, so if you're so if all quantum operators, if all operators are unitary, then Hermitian will imply that it's the reverse of itself. Right? This is the Hermitian. So unitary will imply Hermitian. No, I mean unitary. Sorry. So this is Hermitian. Okay. So Hermitian plus unitary will give you this. Okay. The question is this required for every quantum gate? And he said, no, you don't. And he's using a phase gate as an example. What is a phase gate? Let me just do a simple one like this. This is a phase gate, right? What is its Hermitian? Yeah? Okay. All right, so is this a Hermitian operator? Therefore, that means if I take this, or if I just, yeah. Oh, I see. So if I just multiply this by the other one, it's not a reverse. Okay. So this is 1, this is 0, this is 0, this is 1. Okay. So it looks like it is Hermitian, isn't it? No? Am I confused? But this is 1. Am I doing this wrong?
This is unitary provision. The Hermitian
Oh. Oh. I'm sorry. I'm confused. This is Hermitian. This is unitary. Okay. Right. So this is unitary. And this is Hermitian. Oh, I see. So that's why you say you apply. If you apply this twice, you're supposed to get 1. That is for that is unitary, right? No, this is Hermitian. This is Hermitian. You apply this, so reversible. Reversible. That is a property of Hermitian and unitary. And this is to see if this is okay. Okay, so you don't do this. Okay, I see. Sorry, you're right. So is this if it's Hermitian, then this should equal to that. And obviously they are not. So this is not Hermitian. So she is reminding us that all gates are Hermitian, but they are all unitary. Okay, and unitary means reversible, right? Unitary means reversible. Am I correct? Oh gosh. All right. So you're right. Okay, gosh. Not all gates are Hermitian, but they are all unitary. And you might think this is really boring, but it's not. I'll tell you why. Not all gates are Hermitian, but they are not. Not all gates are Hermitian, but they are unitary. Quantum processor made of many gates. Will be unitary, right? Will be unitary. And we require it also to be Hermitian. Yes, she. We yeah. We require it to be also to be Hermitian, so that the quantum processor is reversible. Reversible. Okay. That's what you're asking, right? So his question is, why do we require quantum processor to be Hermitian if not all the gates are Hermitian? Why do we require the quantum processor to be Hermitian so that it can be reversible? Or in other words, why do we require quantum processor to be reversible at all? That's basically his question. And at the beginning of this lecture, I said that quantum processors, I kind of just stated as a claim. I say all quantum processors are reversible, right? And that's why give us, this problem of one mapping to many. And he's saying right now that this might not be true unless you require it to be reversible. It might not be true, right? Okay. I don't know the answer to your question because I was confused between this unitary and Hermitian condition. I will look it up and I will send everybody an email and explain why do we require quantum processor to be reversible. Yes, Hermitian is a requirement for observables. Well, see, if you take, so basically, processor is a series of gates, right? So if you have like A gate, B gate, C gate, D gate, right? So you just like a number of them goes on up to Z gate, right? You stream them together. That's basically your quantum processor, right? That's your quantum circuit, right? You just basically string up all these gates that you can find in the series. And Han is saying that don't we need to require this? So this is basically an operator, which composed of many operators, right? And so here's his question is, do we need to specify this to be Hermitian because we need it to have observables? Yes? I think we don't. I think we don't because when we take a measurement, we are not taking a measurement of the whole thing. Sometimes we take measurement of this or that. Yeah? We take this measurement or take this measurement. If we want to take measurement of the whole output state, yeah, and then we want the measurement to fall into one of the eigenvalues of this overall operator, then yes, we will have to require it to be Hermitian. But that's not what we generally do. So the Hermitian condition cannot be imposed this way. There must be some other reasons, and I need to find out. Okay, but thank you very much for your suggestion. All right, so great, good, very good. So this is a very subtle issue, and that's if you get all these things figured out, you have a good foundation for quantum computation. If you don't, if you only know how to like do algebras, then you understand nothing. Okay, so it's important. So yes, although it sounds very boring, that's the game what quantum computer scientists play. All right, so now it's 3:26. I'll give you a 5-minute break to get some water, to get refreshed, to wake up, and then we'll come back. Now, I'm asking why quantum processes is reversible. Are they guaranteed to be reversible?
Because the quantum gates are unitary, so if they are unitary, they are guaranteed to be reversible.
If they are unitary is this. If they are unitary.
I think this identity can be proved.
Yeah, if they are unitary, they are guaranteed to be reversible. Reversible is this, right?
No, it exists. This reversible means the existence of the inverse transform.
Oh, I see.
So this self.
Oh. Okay. That's like another thing. So you're saying like some other operator might exist to reverse it, but not itself.
Yeah.
But it's not necessary itself.
Like I already
right?
And the reverse is high
Mm-hmm. Okay, so my condition is this. I don't know what to call it. I call it reversible, but you're saying if this exists, if this exists, then it's called reversible. So it's not necessary in this form. I don't know what to call this. What do you call this? Self-reversible? So my question is really like, is that a guaranteed property for quantum processor or no? If no, then why do we require it?
I think the reversible, the people talking about the existence of inverse transform. So the unitary.
But if you don't know the form of that, then you can, like the proof I just gave, the contradiction proof, right? You cannot do that because you don't know the form of the reversed operator, inverse operator. This is not called, I think this is called inversible. This is like an inverse, right? Inverse operator. So the existence of an inverse operator is this. I think this is reverse. So you apply this twice and it give you back to the original state. This is reverse. So I would call this reversible. You apply this twice and then. Yeah. Inverse generally doesn't have like a known. It doesn't have a known form, right? But a reversible matrix has the inverse as itself.
Like when I'm taking the course, the instruction is reversible means the ability, because there are some matrices they don't exist in inverse matrix.
But how can they not exist? Like you said, if they are unitary, which is guaranteed, then all of them exist.
So for quantum process, it will guarantee to be reversible.
Inversible?
Yeah. I found a name of it.
Its own involuntary. Seriously? It's called involuntary? This is a property called involuntary? Involuntary. Okay. That's very strange. Thank you. Involutory. I never heard of this. Yeah, but I think this is the property we're after.
But I think it will work for the modulus computation. But I'm not sure for all the quantum because if the quantum process only consists of pi over 2 poles, then it will not be involved.
Mm-hmm. All right, I need to look into this. Oh, but thanks. Okay. Who is bored? All right, let's come back to our lecture. Who is bored? Who's not bored? Who find this very exciting? Okay. All right. Do you know? We know that quantum computers is, something that we all desire because it has this parallel capacity, right? Due to superpositions. Now, so suppose you have some state, I don't know, 1, okay. Wait, let me first say something. A quantum processor a qubit can only take 2 values. Yes? So in the computational space, there are only 2 values that you can use, 0 and 1. Yes? Okay. What if you want to represent 2 and 3 and 5? You want to you can use 0 for this, 1 for this. But what if you want to do 3 numbers? 3 different numbers. Do you use a superposition? Like, for example, you call this 0, this 1, and you just kind of randomly assigned numbers to superposition. Do you do that? So if I have like a series of numbers, right? 2 to 10. So do I just randomly assign superposition states of the 2 so that I can represent all of them? Can I do that? Okay. Yeah, I'm running out of ideas. Okay. Okay. Just for example. So is this the idea of quantum computation? You first represent many numbers with different superpositions, and then you try to operate on a superposition of all these superpositions, and then you get your answer once. Can we do this? Well, assigning different combination to different numbers, that is not wrong, I would say. Okay, I can assign an alphabet, 26 letters to numbers, right? It's like Morse's code. It's not wrong. But if you want to put it into a computer, a processor, you probably will run into serious problems because these assignments are kind of random. right? And when processors are like doing stuff between the states, transforming and mapping them, yeah, you probably will not have, you will not, you probably will not have this. Good question. But I want to motivate that first. You see what I'm saying? So you can do like a kind of a random assignment of numbers, mapping your combinations, your superpositions to this states. However, after processing this bits, you might not get a reasonable or sensible result. That's what I'm saying. 2 plus 3 might not be equal to 5. Yeah? So all things that you're familiar with, I'll go away. And you might have like 2 plus 3 equal to 8, and 6 plus 7 is equal to 2. Garbage like this. This is not very useful. And certainly this is not how computer is supposed to work, right? So what do we mean by like leveraging with the power of superposition? Like, where do we do that? Yeah? All right. So, well, first of all, Ting was making a suggestion. She's saying, can we have more bases? Can we have more bases so that we can have like a consistent way to represent all these digits, all these numbers? The answer is yes, we can have more bases. Right now we have 2 bases, right? So it's basically this. We have a set that looks like this. If we have not 1 qubit, but 2 qubits, we have a bigger set, right? They usually represent this as 0, 1 squared. 0, 0, 0, 1, 1, 0, and 1, 1. Okay? So tensor product of the space of 0 and 1. If you expand your basis, how many number can we represent with these bases? 4, right? Again, we can randomly assign this to be 6, this to be 8, this to be 10, and this to be 5. We can do that, but then we will again run into problem like this. We get nonsense after, quantum transformation, quantum processings. So how do we do this in a consistent way? That's the question. And people find that you should. One way you could do this is to use binaries, binary codings. Yeah. So for example, this number in binary coding, what would that be? We practiced this last week. Should I ask the master of binaries? 1, 0, 1, 0. Is that correct? Yes. How about this number? Okay, 1, 1, 0. Good. How about this number? You guys are getting better. How about this number? 1, 0, 1. Yep. Okay, we all know how binary works, right? I don't need to explain it. Therefore, if we need to use binary, if we're using binaries for coding these numbers, then in order to get to 5, we need 3 digits. 10, we need 4 digits, right? 2, on the other hand, only require 2 digits. 3 is also 2 digits, right? So if we just match this binary with this product state basis, yep, we can use this to represent 3, and this represent 2, and this represent 1, this represent 0, correct? All right, so we can have a state that looks like this, and it is actually a product state. We can have a state that looks like this, and it's actually a product state. State that looks like this. So you see, so this is no longer the QB base. Okay, this is the computational base, and this will be that, and this is the 2 qubit base. 3, yeah, and the list can go on. If you want to represent a larger number, you need to increase your base space. Yeah. So for example, this will live in a basis, a 4 qubit state base, right? Because there are 4 digits. Yeah. Okay. So suppose you do this. You have a consistent way of defining, of mapping your state to your qubits, although you're using a lot of qubits to represent the numbers. Okay, that's why a single qubit quantum computer is pretty much useless, because it only can represent 2 numbers. Yeah, 0 and 1. Right. So for the larger number that you want to handle, the more qubits you need. Okay, so if I want to do like calculation between numbers from 0 to 100, and I'm mapping this number to also 0 to 100, right? How many qubits do I need to use? So that's basically saying what is the binary representation of 10, 100. Smart. You're using your phones. Yes. Yeah, that's good. Okay, you can use your phone, because I don't know the answer too. What's the binary coding for 100? Do you have it on top of your head? No, you don't. 7. So what's the coding for it? One 110 110. Is that right?
No,
100. Okay. 110100. So 6 digits. Okay, I trust you. I don't know the answer, but I trust you. This requires a 6 qubit space. Yeah. So your quantum computer, whatever you want to build, your quantum processor, needs to have 6 qubits that work together. You need to have gates that can talk to 6 qubits at the same time. Yeah. All right. So, and how do you know? Do you know the current status of the quantum computation capacity in our country? 5.
In our country?
Yeah. Like
Less than 1.
we have 5 qubits, so we cannot do even 100. Okay? That's all right. We are growing. But I just want you to have a feeling of how these are called quantum registers. Okay? You use multi-qubit bases to represent numbers. Each one of them is a register. Or each digit is a register, like depending on how you want to see it. But that's my point. This is a quantum register, okay? We don't use superposition to code numbers, to code information. Yeah, you can say that. We don't necessarily use superposition to code information. So where do we use superposition? If I have a so let's just stay simple. Let's just stay with a 2-qubit basis, and we have 4 numbers, right? All right. So we have 4 numbers, and this is this is 0, 1, 2, 3, and they are mapping to different. So 3, 2, 1, 0. They are mapping to different numbers. So say this is a computer. A computer provide a function that do the mapping, right? If this is a classical computer, and you want to know if you implement this function with a classical computer, and you want to know certain property about this function, what do you need to do? For example, if you want to know if this function is a constant function, right? So whatever input you give it give you just send output. If you want to do this, what do you need to do? You need to run the calculation how many times? 2 times? 4 times. 4 times. Correct? I need to evaluate this and see if it's equal to 3. See what the numbers is. Okay? If I evaluate this and see what the number is, and say the number is 1, and I evaluate this and see what number is. If the number is 1, yeah, maybe it's like a constant function, but can I be sure? Can I be sure? No, I cannot, because I need to continue, right? Because as soon as I put in 2, fit in 2, it might give me a different number. So I need to exhaust all the space. I need to exhaust all the elements in my space, in my computational space, in order to determine the property of this function, a global property of this function. Yeah? So only if I finish this, I can be sure that this is a constant function. If this is 2, no, this is not a constant function. Okay, but guess how many steps? Okay, so let me say this is 4 steps. 4 rounds, 4 steps, okay? How many steps or how many rounds does a quantum computer need to determine a global property like this? Or let me even exaggerate. If I have a space that is 6 digit, that has 6 digits, okay? A 6-digit space, I have how many combinations? How many? 2 times to the 6, right? And this is a big number. I don't know how big that. I don't know what this number is. Is it? Okay. So 64. Not incredibly big, but big enough. If I want to achieve the same purpose, I need to run my classical computer 64 times. to see if each output is the same number, right? But what about quantum computers? So classical, 64 times. How about quantum computer? Huh? Say again? 1? Like, this could be a quiz problem, man. What do you think? 1. What do you think? Why do you say 1? Convincing. You calculate what? At the center. You calculate 6 qubits at the same time. And then? But any number you find here is represented by 6 qubits. It's a 6 qubit register. So of course you calculate 6 qubits at the same time for one number. But you have 64 numbers. How do you know each one of them have the same functional value? What do you think? You say 1 with confidence. You're guessing? With confidence?
Yes.
Okay. Fine. Phase difference. Okay.
Because if you are trying to say it's not exaggerating, then it must be a very powerful answer.
Gosh. Well, you know what? You guys are right. It is 1. And no matter how big the number space, no matter how big the space is, if you have now like a 10-digit qubit and the number becomes really, really big, right? Classical computer it scales linearly. How many numbers you have in the space, that's how many number of times the classical computer needs to do. But a quantum computer can do it in 1 run.
I have a question. How about the duration of one run?
Yeah, that's a good question. And that depends on the design of the algorithm. How many gates you have, right? Because each gate takes a certain time. So if you have like 1,000 gates, of course, that takes forever. So if you have a good algorithm, an efficient algorithm, that can probably finish the task before the coherence time. Okay? But the reason I tell you with very much confidence that this is 1, not because I guess it, but because I read about it last night. Just kidding. This is basically the problem of Deutsch JASA. For Deutsch JASA algorithm. Okay? So this is the problem. This is a recipe for solving this problem. Okay? Remember? So this is the dumpling, and this is the recipe for making the dumpling. Okay? So right now I think we're ready. And in this algorithm you will see how superposition is used as a quantum advantage to achieve this purpose with only 1 run. Okay? Superposition. So superposition is not used for representing numbers. Superposition is used for processing the states. Okay, and we'll see how that works. To understand how Josh. So in today's lecture, man, this feels like an opening. In today's lecture, we will give an example of just we will not give a general proof of Deutsch-Jozsa algorithm because that involves math that I don't understand. I know it's a very lame reason, but it's okay. It suffices. We will give a demonstration though. We'll give a proof for this, for 2 qubit space. Okay, so it's not trivial to do that, but that served to illustrate how the algorithm works. And if you trust their math, then you can be confident that this will apply to a space of n. Okay, but we will do 2 as an illustration of how this algorithm works to show you that why it works. Okay, but to start with, this will be difficult. So we will start with the precursor of it. So the Deutsch algorithm. The Deutsch algorithm deals with a space of just a space with two bases. Okay. Once we understand how Deutsch algorithm work, we'll go to a space of 4 elements and illustrate how Deutsch-Jozsa algorithm works. Okay, so that's the plan. And if I can finish this before 5, I'll call it a success. And I will need your help. I need your help for what I'm gonna do next. So I need 4 volunteers who want to be the volunteer for a quantum computation lecture. Who is interested? Who still have that passion after 1 semester of torture? Okay, so this is the Deutsch algorithm or the Deutsch construction. Let me just call it Deutsch construction. So he's saying if this is the function that you want to find out, remember the function that we give is this: x, y, x, f of x modulus 2 with y. If this is the function you want to inquire, you want to evaluate, then you put 4 elements, and that's the Deutsch construction. You put 4 elements, actually 5. You first put a Hadamard gate here, a Hadamard gate here, a Hadamard gate here. Okay, and then you put a detector here and a state of 1 here. Yes? Okay. And here you can, in this place, you can have an arbitrary input. That's fine. It doesn't matter. Okay, and this you don't care about, so it just goes. But this 1, 2, 3, 4, 5, this 5th element is what Deutsch construction is about. Yeah. Okay. So this is the algorithm. Done. The algorithm says, this is the construction, and the algorithm says if here you measured unchanged, so unchanged, that means A. If you measure A, the same input that you feed in, then your function is a constant. Unchanged means unchanged means constant. Okay? And well, if it's not constant, then it will, if it's not, for example, so if this is constant, they either take 0 or 1, right? 0 or 1, yes? Okay, if they are not constant, that means if one takes 0, the other must be 1. If one is 1, the other must be 0, right? So they both take a value. So so this is the function. This is the function. This is the space of the input. This is the space of the output, right? If they're constant, both take the same value. If they are not constant, they take different values. One take 1, the other take the other, right? In this scenario, it's balanced because each one take a value. Each value are taken by a type of input, yeah? So we call this balanced. So that's just the language people use. And this is a constant. Okay? So means constant, changed. In this case, changed means because A can, this qubit can only take 2 values, right? 0 and 1. And you don't know, if you give 1, then 1, an output of 1 give you constant, an output of 0 give you balanced. Okay, that's how this works. Means balanced. Okay. So this is the Deutsch algorithm. The problem was to determine whether this is function is constant or balanced. And he said we can do it with only 1 run instead of 2 runs. A classical computer needs to do 2 runs. Okay. Now I want you to do the following. Okay, let's just work with an example. Let's just say this is 0. Okay, working with an example is the best way to understand how this algorithm works. You have heard of Shor's algorithm, right? Shor's algorithm. Have you read about it? My advice, don't read. No. It will make you lose your interest in quantum computation. Okay? Just remain your state of hearing about it. All right, that will keep you interest on. Until you're ready, don't read. But you can play with some examples like we are doing now. Okay? Let's say we have 1, 0, and the 0, 1 state will first go through 2 Hadamard gate, right? So I'm just gonna represent Hadamard gate on the first qubit, Hadamard gate on the second qubit. Yeah? What is the Hadamard gate transformation for 0? You need to remember this by heart. So remember, Hadamard gate is this. It's basically like the identity, except the tail is -1. Okay? And how do you read this? you read it like this. So this is the first combination, this is the second combination, okay? Yep. So 0, which is this is 0, this is 1. 0 will give you the symmetrical combination, yeah? And 1 will give you the anti-symmetrical combination. Or you could say a phase flip, a pi phase on the excitation qubit, on the excited qubit, unexcited state, okay? And don't forget this square, yeah? All right, so this is the first qubit. Let me just label it for now to make it absolutely clear. Now, if we want to prepare it for this function to operate on, we need to separate 1 and 2, right? Yeah. So let's do this. 1 and 2. So that's 1 turn. So 1 and 2. Okay? Yes? Now, let me make it go through the quantum processor. What would this do? It will remain, after the quantum processor, the first qubit will remain its value. Yes? And the second qubit will change value to f of x. And x is from the first qubit. So it's this. Sorry. 1, 0. 2, 1, 1, and 2. Is that right? Yes, that's right. Correct? All right, so this here, the wave function is 1. Here the state is 2. Here the state is 3. Here the state is 4. Yeah? All right, so this is the first state. This is the second state, right? And this is the third state. Yes. Okay? Now, we don't know. By the way, do you see that there are so many states here in the superposition? That's that we're doing quantum computing right now. This is where the superposition is used. Okay? All right, but that's not getting too overexcited. Let's just stick with our task. Now I need 4 volunteers. Who want to be my volunteer? Oh, come on. Who want to be my volunteer? Oh, thank you, Mark. Thank you so much. 1. I need 2, 3 more. There are only five of you left. Okay, that's Han. Thank you. Who else? We have only one girl in the room today, right? And according to the equality principle, we must invite her. Otherwise, that would be discrimination.
No, asking me is discrimination.
No. Okay, why don't you go up, him, and then one more from you, because you give me the most trouble today. All right. So I want you to do the following. I want you to discuss 4 cases. 4 possible cases. So we're basically here, like we are exhausting all the possibilities, right? So this is balanced. Sorry, this is constant. These 2 are constant, but one take a value, the other take another value, right? We just want to run through all kinds of possibilities to see how this algorithm works. That's our purpose today. We're not here to prove it. We're here to understand it. Yeah? So let's do this. And it won't be so hard for you, I'm sure. This is nothing but okay. So this is constant. A and B are constant. C and D are balanced, right? Four possibilities that you can possibly have. 4 scenarios. And let's see if why this can determine whether F is constant or balanced by measuring the X qubit, the first qubit. Of course, after the Hadamard gate, but by measuring the X qubit, okay? So by measuring X qubit, after this steps 1, 2, 3, 4. After the 3 steps, 1, 2, 3, and you measure the first qubit, you can determine whether your function is balanced or constant. And now we want to see why it is this way by just putting the values in and see what you get. Okay? So 1, 2, 3, 4. Come on up. Choose your problem and work out the math according to this. Okay? Don't forget to use, well, you don't need to use the cheat sheet. This is simple enough. Oh man, it's good I can get to sit. You can forget about the subscript. You don't need to label the subscript. I can tell by the position. Yeah, the subscript 1 and 2. You don't have to. You can if you want, but you don't have to. Yeah. I'm sorry. That was a typo. Are you calculating in your mind?
No.
She's using her quantum computer, her quantum processor to neural quantum computer. I like that name. I think it's more fun to do this calculation yourself than watching me do the calculation. Yeah, they will do the 2-qubit ones.
Okay.
I would like to ask you to group the first qubit. I would like to ask you to group the second qubit or according to the first qubit. So if your first qubit is 0, group all of them with the first qubit that are 0. You see, because later we're gonna do an operation on the first qubit. So I would like you to group them. Like for example, this one, I would like to have the first one factor out and group the second qubit together. You see what I'm saying? Okay. So Han, you are doing the opposite. Wait. So 3. So 0. Oh, no. Actually,
I can group this together.
wait. Yours is 0. So 0, 1, 0, 1. Oh, like this is right, but you can do one step further because these two are the same, right?
Yeah.
Yeah. So why don't you do that? You-
I
you-
think the
you-
result is the same.
No, please. I want to
Okay.
I want consistency with all calculations. Are you grouped in then?
The 0, 1 and 0, 0.
Yeah, they are the same, right? So they can be factored out. This is breaking. This is breaking then. I want you to group them as much as you can. Yeah, group them into two groups, 1 and 2. Yeah, this is good. Yeah, this is what I want. Cool, thank you. Yay.
对啊。哦，对。
See, now they are like helping you because they don't want to do 2 qubits. Right, thank you, Han. You group this, so they are the same, right? You take them out. I want 2 terms like this. This is 1, this is 2. A product of 2 qubits. I want a product of 2 qubits. Okay, like this. This is good. 1 and 2. Product of 2 qubits. Good. Thank you. Okay. Good. All right. Okay, great. Thank you very much. Okay. Well, first of all, I want you to notice one thing. You see all these 4 results. All of them have their final state as a product. They have 1 and 2, right? 1 is the superposition, 2 is the superposition, right? 1 and 2. Okay? 1 and 2. 1 and 2. Yes? What is common between all 4 cases? What's the common element between among these 4 results? Which qubit? The second qubit, right? The second qubit has 1 minus 0 or 0 minus 1. The symmetric state, the symmetric superposition, right? That's the second qubit. Okay, so that's one first observation. Second observation, besides this, what's the common element between these 2 results? In the first qubit, they have both have 0 plus 1, right? And here, what's the common, besides the second? In the first qubit, they both have 0 minus 1 or 1 minus 0, right? 0 minus 1 and 1 minus 0, they are only different by a global sign of minus. So that's okay. It doesn't matter. So they are basically the same state, right? So you see, the thing that distinguishes this case and this case is in the first qubit or second qubit. The second qubit are the same for all of them. But the first qubit is different. The first qubit for the balance function is antisymmetric, right? It's antisymmetric. They have the same form. The first qubit for the constant is symmetric. Yes? Okay, now I want you to know that there's one more thing. The Hadamard gate is reversible according to Wayne's definition. According to my terminology, it is reversible. Okay, you can just show yourself simply by multiplying these two matrices together, and then you will see that it is equal to 1. Yeah. So if it is reversible, then that's easy, right? Because now we're going to apply a Hadamard gate on the first qubit, right? So this one will go to what value? 0. Yep. Sorry. This one will also go to 0. 0 minus 1 will go to 1. Yeah? And this is 1 minus 0. So this is basically 1 with the minus sign. Yes? Okay? So that's this. After the Hadamard gate, right? So after the Hadamard, because what distinguishes this case, these two groups, is the first qubit. So you apply the Hadamard gate on the first qubit. Yeah? And if you get 0, then that means your 0 is unchanged, right? Because the initial state of the first qubit is 0. So if you get 0 as your output, as your detection, you get constant function. You see? Constant function. Right? This is not a proof, this is just a demonstration. And this is a balance function. Balance function gives you a changed state. So a state that is different from your input, which is 1. Yeah? Got it? Okay. Now, what if, so we have shown that this state works. What about, because this is an element in Deutsch's algorithm, so you don't change this, okay? But the other one, you can have, right? You can do 1, 1. And you can do this all over again. Who wants to do that? No one is interested? Okay. So I'm not interested too either. But I will show you another way. So instead of exhausting all these possibilities, I will show you another way, and using this, you can do 1, 1 very fast. Okay? All right, but thank you very much for your helps. I'm gonna repeat your calculation one more time, but with a slightly different method. All right. I'm gonna use my cheat sheet. Okay? So this is equal to 0. Okay, so anything that is modulus with 0 is itself. Anything that's modulus with 1, that's the inverse. Okay? So here we have 0, inverse, 1, and inverse. Yeah? You get it? Okay, now we discuss. So if this is constant, right? If it's a constant, if this is a constant, then, so let me just call this 1, equation 1. So equation 1 will be, you can replace the second row by the first row. Do you agree? If this is a constant, then these two states are the same. These two states are the same. You agree, right? And this will be just this. Yeah. So this is qubit 1. This is qubit 2. And then after the Hadamard gate on qubit 1, yeah, this will transform to 0. Yep. So you see, constant, same, right? Same value on the first qubit indicates constant. What about balanced? Balanced means this is unequal to that, right? And since the space is limited only to two numbers, this basically means or I would say 1 is equal to the inverse of that, right? Because whatever value f0 of f over 0 takes, f of 1 will take the other value, which is the inverse of that. Yeah? Agree? So this will mean, actually, I should probably write A and B. Okay, so this will mean that this 2 so we keep this first one. For the second one, this will be the inverse. This will be the inverse. And the other one will be f0. The inverse of the inverse is f0. Okay? Okay, so this is not hard to see, right? You see this and this, they are different by minus sign. Yes? So you take out the minus sign and it will become this. This is the first qubit, this is the second qubit, right? And the Hermitian, the Hadamard gate here will transform the first qubit. Since it is antisymmetric, with the minus sign coming from this balance property, this will become 1. Two, 1. Okay? So you see, the first qubit here has a different value from your input. So that's the balanced. Okay. All right. So now, if you want, you could try this. Okay. You can try this, and just to show yourself, this means here you have a minus sign, right? This means here you have a minus sign, correct? This means here you have a minus sign. Minus sign, yes? And basically you do nothing but change your minus sign here, right? So 0 minus 1. After the Hadamard, 0 minus 1 is what? 1. Yeah? The same as your input, right? Balanced. Constant. Yeah? Here, you do the same. Here it's minus. Minus, and this is a plus, right? Plus will give you 0. Different for balance function. You see? Proved. Or showed. Okay? So you see, using this, it's much easier. Okay. So now I see that you're all well prepared. You're ready for the Deutsch algorithm, which is fantastic because there are 2 pages. We're almost done. We're not going to do the optical implementation. I'm sorry. Maybe I'll do it next lecture together with the talk, hopefully. I try to save you more time for the final week. Okay. So, 8. Deutsch algorithm or construction. Okay. So remember I said this is a generalization of the Deutsch algorithm. The Deutsch algorithm has map a space of 0, 1 to the power of 1 to 0, 1, right? To generalize this, you want to do however large the space is, you're going to map it to here. Yeah? Okay? So if we have this to equal to 2, that means we have 0, 0, 0, 1, 1, 0, and 1, 1. Yeah? And each of them can represent a number. It doesn't matter. Okay, but let's now stick with the space, the physical base. Okay. Now the question is, do they all have the same value, or can they? So the problem is the problem is now phrased a little differently, because previously we have only two elements, right? If one element take one, the other must take the other, right? So it's pretty easily stated. But now the problem is phrased a little different. So either you have everybody. So this is constant. Sorry. Everybody have the same value. Or you have half of them. And it doesn't matter which one. So for example, you can have this equal to this, and they take one value. And the other two take the same value, but that value is different from the first group. Okay, so the balance condition now is, now you can see why it is balanced. You see, because 2 volt goes to 0, and another 2 volt goes to 1. It's balanced. Okay, so the balance condition now is making more sense now, right? So if you have like a space of 6, 10 to the 6, you have 64, right? A balance condition will be 32 of them, 32 of the element will map to 0, or will vote for 0. And the other 32 will vote for 1. Okay, balanced. Okay, so that's just one example to illustrate what balance means. All right. And now, since we have a 2-qubit state, our function needs to take 2 input instead of 1. Sorry, 3 input instead of 2. Okay, so x1 and x2. And this is y. We still have just y, one y. Okay, and then here the output is the same. The first two remain the same, but the third one will have f as a function of the product states. So let me just write it in this way. Okay, so this is the f function for the product state modulus with y. Okay, so this is just a generalization of a quantum processor, a generalized quantum processor. Now, the Deutsch-Jozsa construction is basically the same as the Deutsch construction. So what do you need here? Is Hadamard, right? And here you also have a Hadamard. And here you also have Hadamard. Many Hadamard, right? And here you have a detection that look at the product state. Okay? And here you have an input of 1. So this is the Deutsch-Jozsa construction. And here you can have any input you want. And for now, we're going to try. So this is A, this is B. And for our purpose, I'm going to just do a demonstration. So we're going to ask this to be 0 and this to be 0. Yeah. By the way, now I have this, right? You can try to show for yourself if you break the Deutsch construction, if you replace this 1 by 0, for example, and you can see if it works. Yeah, I won't go into that because I'm running out of time. But you can replace this with 0 and you can see if it works. And it won't. And that's why that 1 is the necessary element in the Deutsch construction. Okay? All right, so let's do this. So we're gonna follow basically that. And we're so that we can be more efficient with our time. So now I have a 3-qubit state, right? 1, 1, 0, 0, 1. So this is the first 2 qubits, and this is the 3rd qubit. Yeah. So going through Hadamard gate 1, Hadamard gate 2, Hadamard gate on the 3rd qubit, I will have a superposition of 1, the symmetric 1, for the first 2 qubit, and an anti-symmetric 1 for the 2nd qubit. Right? And of course, I like to group this into a product state because later I'm going to do this, right? And I need to know what my product state is. So this gives you 1, 1, 0, 0, 0, 1, 1, 0, and 1, 1. Okay. Yep. Again, we need to break it to 2 products.